It was a standard plant outage at a containerboard mill in Louisiana. Contract workers were performing routine maintenance above a large storage tank when a stray spark found its way into an explosive atmosphere. This 3D trajectory map shows the sheer mechanical force of the resulting blast. The 100,000-gallon vessel launched directly over a 6-story building, eventually crashing into process equipment 375 feet away. 3 contractors working nearby were killed instantly, and 7 others were injured. The workers on the platform that day were conducting hot work, welding and grinding, on clean water piping. The pipe was completely disconnected from the chemical systems. By all standard operational measures, they were doing exactly what they were supposed to do, in an area cleared for work. But sitting right below their work platform was a massive vessel known as a foul condensate tank.
It acted as a collection point for condensed vapors, holding mostly water, but also a floating layer of highly flammable turpentine. The explosion at DeRidder was a result of a predictable chain of invisible systemic failures that were left unaddressed, despite existing industry warnings. Looking at this cross-section of the tank, you can see how it operates safely under normal conditions. The dense vapor cloud at the top of the tank is maintained above the upper explosive limit, or UEL. The UEL is the maximum concentration of a gas in the air that can burn. Above this limit, the mixture is too rich to ignite because it lacks enough oxygen. During the mill's annual shutdown, the non-condensable gas vacuum system, which normally extracts these vapors and routes them to a boiler, was powered off. Without the active process running, the liquid inside the tank began to cool, altering the internal environment. As the internal contents cooled and contracted, a vacuum formed inside the vessel. This vacuum physically pulled fresh air into the tank through a pressure vacuum breaker on the roof. Once that fresh oxygen mixed with the rich turpentine vapors, the internal atmosphere dropped below the UEL and became highly explosive. The mill lacked clear operational ownership for the foul condensate tank. Because no specific department was assigned to manage the vessel during the outage, no one monitored its status, and no one realized the internal chemistry had turned the tank into a bomb. When an industrial facility transitions from a steady operating state to a maintenance shutdown, the physical chemistry inside the equipment actively changes. Failing to track those environmental changes creates deadly traps for the people working around them. On the morning of February 8th, a safety coordinator initiated a hot work permit to authorize the welding repairs. The permit thoroughly evaluated the water piping, the pipe bridge, and the surrounding catwalk platform, but it completely ignored the 100,000-gallon tank sitting immediately below the work zone. This top-down schematic illustrates the flaw in the pre-work safety check. A mill employee used a handheld combustible gas detector to check the ambient air up on the pipe rack, found 0% of the lower explosive limit, and issued the permit. They never tested the air inside the massive tank sitting just feet away. Corporate knowledge regarding the tank's explosive potential was severely lacking on the ground floor. Many of the mill's own operators believed the tank was a perfectly sealed system that could never pull in air. Without understanding the hazard themselves, they had no way to warn the outside contractors about the risk. Relying exclusively on administrative paperwork to evaluate hazards leaves a massive margin for human error. Active engineering controls, like automatically purging the tank with nitrogen gas to mechanically displace oxygen, remove the possibility of a fire entirely. A localized ambient air check provides zero protection if supervisors fail to evaluate the massive fuel sources sitting inches away from the falling sparks. The mechanical design of the tank actively allowed air to enter during a shutdown. Why wasn't this hazard identified and engineered out of the process years before the contractors arrived? OSHA's Process Safety Management, or PSM, is a set of regulations designed to prevent the release of highly hazardous chemicals. PSM requires companies to conduct rigorous hazard analyses on processes involving these materials. However, because the total volume of flammable liquids in this specific gas system fell below the legal threshold quantities, the PSM standard did not apply. Because the law didn't mandate it, PCA chose not to voluntarily include the non-condensable gas system in its safety program. No formal process hazard analysis was ever performed on the foul condensate tank. Treating minimum legal compliance as an organization's ultimate safety ceiling guarantees they will remain blind to catastrophic risks. 3 people died at the DeRidder mill because systemic hazards went unchecked, uncommunicated, and unanalyzed. While the spark was the trigger, the underlying cause was a failure to manage the invisible risks of the shutdown. Preventing this requires expanding permits to test vessels within a 35-foot radius. Second, mandate joint hazard reviews between operators and contractors to discuss failure modes. Finally, voluntarily apply process safety management to all high-consequence systems, regardless of regulatory thresholds. Surviving a routine maintenance shutdown requires actively hunting for the hidden dangers the rulebook doesn't force you to see.